Hello and welcome. Today we'll dive into mesh analysis for an RLC circuit, and I'm going to walk you through each step from calculating the impedance to understanding power calculations. This method is crucial for analyzing circuits that include reactive components like capacitors and inductors, which are essential in real-world electrical systems. This is the circuits that we will use for our calculation. 100V voltage source, R1 is equal to 50 ohm, R2 is equal to 25 ohm, our inductor is L equal to 100 millihenries, and our capacitor C equal to 100 microfarads. Before we start solving for the mesh current, let's calculate the impedance Z of the capacitor and inductor. Impedance is a measure of how much a component resists the flow of current, but it also accounts for the phase difference between the current and voltage. The impedance of the capacitor is calculated using the formula 1 over j omega c. However, the impedance for the inductor is calculated as j omega L, where omega is 2 pi f. By calculating these impedance values, we set the foundation for mesh analysis and get a clearer understanding of how these reactive components impact our current flow. Mesh analysis is a powerful technique, not just for solving this specific circuit, but it also crucial in real-world applications, such as designing power systems and analyzing complex electronic circuits. Learning how to solve these circuits allow engineers to optimize energy flow, improve systems efficiency, and minimize losses. The ability to apply these methods is a skill that continues to evolve in the ever-changing world of technology. Next, we assign mesh currents to each loop in the circuit. These are typically labeled I1, I2, and I3. Mesh currents represent the total current flowing in each loop. Assigning mesh currents is a fundamental step in mesh analysis that simplifies the problem by breaking down complex circuits into individual current paths. Now, we will apply Kirchhoff's voltage law in each loop. The KVL states that the sum of the voltage drops around any closed loop must be equal to 0. For each mesh, we will write KVL equations considering both the resistive and reactive components. This results in a system of equations for the mesh currents I1, I2, and I3. Once we've set up the equations, the next step is to solve them. This can be done using the inverse matrix method. This technique simplifies the process by representing the system of equations as a matrix, which we can then invert to find the values of the mesh current. Now is solving it for I1, I2, and I3. After applying the inverse matrix method, we will get the mesh currents as follows. These are the currents flowing through each loop of the circuit. Solving these currents is crucial as it sets up to calculate voltage and power. Understanding these currents is important not just for this circuit, but for any electrical system where multiple loops exist. Mesh analysis provides a way to understand the interaction between current, voltage, and impedance, enabling engineers to troubleshoot and design more efficient systems. This is a skill that we will continue to be important throughout my career and in the development of new technology. Now that we have the mesh currents for each loop, we can calculate the voltage across each component using Ohm's law. For resistive components, we use V equal to IR, and for reactive components like inductors and capacitors, we use V equal to IZ, where Z is impedance. Let's calculate the voltage R1 and R2. Now let's calculate the P, Q, S, and the power factor of the power supply. P is the active power, while Q is the reactive power, and S for the apparent power. Next is the calculation of P, Q, S, and power factor of R1. Next is the calculation for R2. The calculation for capacitor, and the calculation for inductor. While calculating these parameters is critical, the real takeaway here is the practical application of mesh analysis in various fields, whether it's for designing electrical grids, optimizing power distribution in renewable energy systems, or enhancing the performance of electronics. Mesh analysis is a versatile and powerful tool that engineers use to ensure system operates at peak efficiency. In conclusion, we've walked through mesh analysis for an RLC circuit, calculated the mesh currents, voltages, and power parameters. We have also explored the importance of impedance and how it affects circuit performance. By understanding and applying these concepts, we can design and optimize electrical systems for the future.